So I think yes. All right. I think we can wait for time to.
Yes, sir. Yes, sir.
Yeah. So what is the temperature there? How hot or cold is it there now?
Yeah, today is relatively colder, maybe around 13, 14 probably.
Okay.
And we are at Tezpur, so it is relatively colder than other cities, and this is around 10 kilometers from the city.
Okay.
In fact, Tezpur town. So
I see.
this is relatively colder, and we have greenery surrounding it, just like IISc. Two, 3 degrees lesser than the city.
Correct. But IISc is challenged. I know a lot of things outside, and even within the campus, there's been a lot of other growth and things like that. Yeah.
Yes, yes.
So our campus is quite similar to IISc.
Nice, sir.
Lot of greeneries and surrounded by rivers and all.
Very good. Nice.
Yeah, even the mountains, Himalayas peaks you can see.
Oh, great. I've heard about it. I think that that sanctuary is also not very far away from you. Know that
yes,
Jane was also mentioning that.
Kaziranga.
Yeah.
Yes, sir. In that meeting I was there.
Yeah. I've heard a lot about your campus, and
we are planning to invite you to our campus.
okay, I've been very happy to be there.
Take out some time.
Yeah, sure. Because how I knew is, your university people have been conducting exams here for many years. I mean, they used to conduct the entrance exam,
Yes.
15 years back.
Yes.
So I've kind of bumped onto somebody at some time, etc. there.
Okay.
So something in relation to that, yeah.
Yes, it will be nice if you can visit us sometime.
Sure, sir. We'll see that. Very happy that, okay, we'll be happy to be there sometime. Let's
we'll give
when time works out, yeah. So what is this kind of webinar series? Is it a general kind of this thing for the department, or what is that? Is that an kind of an annual activity, or what is it?
This is actually a part of our Silver Jubilee year.
I see. Okay.
Yes, that's why most of the departments, they are conducting series of this kind of webinars or alumni talk, and so we are happy that we are able to do this.
Very nice. So do we get started, Professor Roy, Professor Baruah, or the other way?
Yeah, so we have 15 students here, and few of them are in the YouTube links.
Okay.
I think we can start, and students will join.
Okay.
Students are joining slowly. Yeah.
Okay. Can you just ask them to kind of introduce themselves? I mean, whoever is in a position to introduce, so that might just take a few minutes, and that would be a good start.
Yeah.
I will start by introducing myself. Okay. Yes, my name is. I think you're all able to see my video now. Yeah. So
Yes.
my name is G. Narayanan, and I'm a professor of electrical engineering. So I studied in College of Engineering, Guindy in Chennai. Then I studied at IIT Kharagpur. Then I did my PhD at Indian Institute of Science. So I've been on the faculty of IISc EE department for about 18 years now. So I work in the area of power electronics, electrical machines, and motor control. So that's almost about me. Maybe you should ask Professor Roy or Professor Baruah should start, and then others can introduce themselves.
Yeah. Professor Roy, please.
Yeah. Yes, sir. Actually, I was supposed to give introduction about you.
That's okay. There's nothing more to introduce. Yeah.
If we are happy and we are lucky
really from the other side. Overall, there on the other side. See, I'm not able to see you. You're all in Tezpur. I'm in Bangalore, right?
Yes, sir.
Yeah.
Yeah. Actually, no. We are happy that we have a great person like you. We are speaking today on a very, important topic on power electronics. So, you already, introduced yourself. So, nothing. I do not want to go further. So I am Professor Shaumik Roy. I am working in the ECE department as professor. My research areas are in neuroengineering or bioneuroengineering, and presently I am also looking after the department of electrical engineering as HOD in charge. Because electrical engineering is a relatively new department, we do not have senior faculty. Slowly people are joining. So that's all about me, and now I think Dr. Ratul Baruah.
Yeah, so I'm Ratul. I did my PhD from IIT Guwahati and postdoc from Purdue University, all in electronics and electrical engineering. And I was also at IISc for a year or so, slightly more than 1 year, as senior research fellow at CEDT. With Professor Santanu Mahapatra.
Okay.
So I was there, and I was to join PhD there, but at the same time, I got a job here and then came back. So this is all about me. So I am working here on nano electronics and flexible electronics here, and still I am in good touch with Professor Mahapatra. So he usually gives lectures here online mode. Recently, we had a webinar series, maybe a few months back. Last year. So he was here for a talk. So this is about me. So students can introduce yourself very shortly, maybe.
Yeah. Go ahead.
Some of you.
Yeah, all of them who are here can. So only about 20 of them or so. So quickly, yeah. If they are possible to turn on the video for a minute, that would be great too. Go ahead. Yes, Deborah.
Good afternoon, sir. Good afternoon, Shaumik sir. Good afternoon, Ratul sir. Sir, I'm in the third semester of my PhD, fourth semester of my PhD. So I'm pursuing a PhD under Professor Bhavesh Dega sir. So my area of research is computer vision and image processing, sir.
Okay.
Thank you, sir.
Very good. Thanks a lot. Good to see you. Yeah. So some of are leaving the meeting. Hope that is not because they have been asked to introduce themselves. Yeah. Others, please can introduce, follow Debaruns. Yes, Prachuria. Go ahead. Yeah.
Good afternoon, sir.
Good afternoon, Prachuria.
I'm in the fourth semester of my MTech. My project guide is Dr. Rupam Goswami, and my research area is Semiconductor Devices.
Okay.
And I'm recently doing my research on FinTech.
Very good. I'm muting myself. Yeah. Go ahead. Next question. Yeah. Thanks. It helps to know your background. Yeah. Go ahead. Yeah.
Rajari-san, I can see you. If you can introduce.
Debarun, you can mute yourself now.
Good afternoon, sir.
Good afternoon, Sam. Go ahead.
Yes, my name is Sam. Most of the teacher call me Rajagisam, sir, and I'm fourth semester student, electronics department. I am international student. I come from Madagascar. Thank you, sir.
Yes, Ananya Bhattacharji, please go ahead. Yeah.
Good afternoon, sir. Good afternoon, Shomik sir. Good afternoon, Ratul sir. I am a fourth semester PhD student, and I'm working under the supervision of Dr. Ratul Baruah sir. And my research area is based on flexible electronics.
Electronics people there. Huh? Thanks to Baruah. Okay, good. Thanks a lot. And Akash Bhagwati, I think you are turned on. And
yeah. Good evening, sir. I am Akash Bhagwati. I am a student of MTech first sem on electronics department.
Mm-hmm.
Yes, sir.
Okay, good. What is the subject? MTech in?
Electronics design and technology.
Okay, very good, very good. Yeah. Okay, sure. Nice to see you. Yeah, somebody came in.
Sir.
Yeah.
Sir, I'm Bhaskarati Varman. I am the MTech first sem student in electronics design and technology.
Electronics design and technology. Oh, okay. Okay, very good. There is one there. Okay, nice, great.
We have one more faculty.
Good evening, sir.
Yes, sir.
Myself, Raja Chitri from Electronics and Communication Department, 4th semester, Tezpur University.
Okay, nice to see you. Welcome. Yeah.
Dr. Rajiv Biswas.
Yeah, somebody came in.
Yes, sir. Me only. I requested Dr. Rajiv Biswas. He is also one of the faculty from Tezpur University.
Okay.
Please join.
Yes.
Rajiv, you are here?
He is locked in. Anyway, we can go to Rupam, Dr. Rupam Goswami.
Yeah. Rupam has been writing to me regularly.
Yes, sir.
Good afternoon, sir.
Good afternoon. Yeah.
Yes, sir. So this is Rupam Goswami. I am an assistant professor here at the Department of ECE, Tezpur University. I have done my PhD and MTech from NIT Silchar.
Very good. Very nice.
Yeah. So thereafter, I have served in Bij Pilani first, and then I have joined here.
Very good. Nice. So what's your area of research? You said?
Yeah, my area of research is simulation and modeling of microelectronic and nanoelectronic devices.
Okay. Very good. Very good. Nice. Great.
Thank you, sir. Thank you.
Yeah. So, any others? For a few more minutes. Yeah. It's good to know as many people as we can. So they don't.
Yes. I request Anita Gupta.
Good afternoon, sir.
Good afternoon.
My name is myself Anita Gupta, and I'm doing PhD under the supervision of Professor Santanu Sharma, sir. And my research area is bioelectronics devices.
Okay, power electronic devices. You said. Okay.
Sir, bioelectronic devices.
Bioelectronic devices. Okay, I'm tuned to hear it as power electronics. Sorry about that. Thank you very much. Nice seeing you. Yeah.
Thank you, sir.
Thanks a lot. Yeah. Yeah. Anybody else? Just feel free. I think that's it's a conversation. Yeah. Yes, Geetika.
Good afternoon, sir.
Good afternoon.
So I'm Geetika Gogoi. And right now I'm pursuing my MTech in electronic and electronic device.
Oh, very good.
First semester.
First semester. Okay.
Yes, sir.
You are in Tezpur yet, or you are attending from home?
Tezpur.
You are Tezpur. You are composed.
No, sir. Actually, I'm attending class from home.
Home, okay. But your home itself is in Tezpur. Okay.
No, sir. In Guwahati.
Okay. All right. Okay. Good. Great.
So situation is not yet that good. It's improving. So many students are having COVID, and many of them are from taking classes from home. And a few students, PhD students and project students, they are in the campus. So
yes. Okay.
Yeah, things are improving. Students are coming to hostels now.
Good. Yeah, let them take their time.
Good afternoon, sir.
Yeah, go ahead.
Good afternoon, sir.
Good afternoon.
Sir, I'm in BTech, like in the first year. I'm doing like ECE. I'm in the ECE department. So like I'm in the first year. Like it's a new experience for me. So
okay, so I can welcome you to Tezpur University itself then.
Thank you, sir.
Very good. Welcome.
Thank you, sir.
Yeah, welcome to Academia. Welcome to Tezpur. Yeah. Okay. Good.
Thank you, sir.
Yeah. Okay. Anybody else? Yeah. Anybody else? Just feel absolutely free. Yeah, come in.
Good afternoon, sir.
Yeah. Good afternoon.
Sir, I am Nivedita Talukdar. I am from first semester from the Department of Electronics Design and Technology. I am doing MTech here.
Very good. Very good. Nice.
Thank you, sir.
Yeah. Good to see you. Yeah.
Thank you, sir.
Actually, we have almost 400 students registered this time, and they are from 6 different countries, so other than India.
Oh, okay.
And they are in actually mostly those students are in UT So
yeah,
that's good.
Very good. Very good. All right. Yeah. Okay.
So probably we have almost 40 students now. We can start.
Sure. Go ahead. Yeah.
So with this, I welcome all of you to the 4th day of this webinar series. I welcome Narayanan sir, and I hand over this session to continue with Dr. Roy. So over to Dr. Roy, please.
Yes, sir. Good afternoon again to all, and welcome all to this session of the program webinar series. We are lucky that we have a very great person today who will speak on power electronics, Professor G. Narayanan. So before wasting more time, already sir has introduced about himself. So I'll request sir to continue to this session on the topic power electronics.
Yes. Okay, thank you all. Thank you, and thanks to Tezpur University. Thanks to the electronics department. Thanks to everybody there for having me for this now. So I think probably we may go on for about 45 minutes or so from now, and anytime you just raise a question, because your backgrounds are different and I don't know what exactly would interest you. And one of the reasons why I wanted this introduction is also to see where you are coming from, what are your background, etc., so that I can be slightly better than in addressing things and guessing what you might be interested in, etc. Yes, and I think you can feel free to raise your hands. I think Professor Roy, that's a way to do that, right? They can raise their hands and pose a question anytime they're interested in. Okay, this is just a conversation. This is just a discussion. Okay, don't take it as a lecture and somebody going to drone and go on like this, right? Okay, so feel absolutely free, right? Okay, just stop me anytime. Anything that is not there. You are not getting a term, you're not understanding, or you have some questions. Yes, please do that. Okay. Yeah, so it's not that what all we are going to cover, that's only going to be burden. It all depends on how well we cover and kind of how much we understand and digest and how well we enjoy. Okay, that's most important. So I hope that you get my point, and it's always challenging to talk to people, and people of diverse backgrounds, and also you're all very far away from me, and I'm used to like many other professors, I'm also used to speaking when a lot of people are around. But let me do my best, and please, stop me whenever you have a question or anything like that. So I'm just going to share my presentation slides with you. So one of you please confirm if you are able to see this now.
Yes, sir, it is visible.
Thank you very much. So I hope the cursor also is visible, right?
Yes, sir, it's visible.
Maybe presenter option, I can probably use a laser pointer. That might work better for you, right? It might be better. Okay. Yes. So, let me just ask a question. Anybody can turn on your microphone and answer this. Okay, you can just see something written there. Okay, I've already told you I'm G. Narayanan. I'm from the Electrical Engineering Institute of Science in Bangalore. and I'm happy to be part of this electronic devices and systems for next generation, ElDeS, what you call as a webinar series. Okay, now this title is there. Okay, so it's not exactly what you're all into, something related to that, etc. Can anybody, any of the students, for example, can just turn on your microphone and say what you think about this? Anybody, just feel free. Your random thoughts on that, whatever you think it might be there.
Students, please answer.
Okay. Anybody, go ahead. Whatever you think. Yes, go ahead, please.
So different variations of power electronic structures that will run a motor.
Very good. So you are catching exactly from the point that it is for motor, right? Okay.
Yes, sir.
So this is all what you are thinking is it's something that is going to be feeding a motor. So there's a power electronic converter feeding a motor and different kind of structures. That's what you say here, right? Okay, very good, great. Yeah. Anybody else? So can you tell your name also? Whoever spoke just now. I'll normally.
Sir, Priyam.
Huh?
Sir, Priyam Pathak.
Priyam Pathak. Okay, I'm normally be very happy to know your names as well as faces. No, I cannot see faces, but let me at least see your names. Thank you very much, Priyam. Anybody else?
Thank you, sir.
Anybody else? Whatever you think out of this. Anybody? Just feel free. Okay. Okay. All right. So as he said, you caught from the point that it is motor. Okay. What does a motor do? It converts electrical power into mechanical power, as you know that very well. So here, and what is a motor drive? You control the input that is fed to a motor. Okay. Like the voltage that is applied, or the frequency, or both the voltage and the frequency, or many such things that you change. So you control the input to the motor, and thereby you control the operation. You can make it run at so many speeds. You can make it deliver different values of torque, and so on and so forth. Okay. Now, I'm not going to be talking more about motor now, except for a few minutes from now, right? So motor, you can imagine one way. Motor can, every motor is a source of mechanical power. So it can run up to certain speed, some maximum speed, safe maximum speed. And it can deliver certain amount of torque, what is called as rated torque. So typically the motor will have a characteristics. There will be a torque speed characteristic. What the motor drive does is it changes the torque speed characteristic into many things. Just as you imagine a BJT, you imagine a MOSFET. What happens in a BJT? If you change the base current, instead of 1 milliampere, you give 2 milliampere, your power characteristics, your VCE versus IC changes. Similarly, in a MOSFET, you change your VGS. Okay, make it from 3 volts, make it 3.5 volts, your gate source voltage. Your ID versus VDS characteristics changes. So similarly, by changing certain inputs, it's possible for you to change the motor characteristics. And you can make the motor run wherever you want. Okay, any speed between 0 to full speed, and it can deliver any torque between 0 to full torque. You can, by moving the characteristics wherever you want. And just as in electronics, you have the characteristic where the motor operates. You cannot change the load characteristics, but you can change the motor characteristics. You can make the motor characteristics shift it left, right, top, many ways, depends on the kind of motor, right? And you can make the motor operate at any speed, all the way from 0 to full speed. Let us say, let's call it as a 1000 RPM motor, or 1500 RPM motor. You can make it run from 0 to 1500 RPM. And you can make it deliver any torque. Let's say 20 Newton meter is the maximum torque, or the rated torque. Anywhere between 0 to 20 Newton meter, you can make it deliver. You can make the motor spin in the opposite direction also, and you can make the motor become a generator also, momentarily for a certain amount of time, or even for a longer period of time. So all this is possible. And how this is all possible? By controlling the input to the motor using a power electronic converter. So this is all I'm going to talk about motor drive today, because many of your background is not from that. I will focus on this portion of power electronic converter topologies. Okay, what kind of power electronic converters, can be used, or something to give you a starting idea on this now. Okay, this is just my start. Okay, I always welcome feedback. Okay, now can somebody, if there is anything, but I'm unable to see any questions, hands being raised. How do I do that? Professor Roy, will you do that for me?
Sir, yes.
Yeah.
If they raise questions, I'll pass it to you.
No problem. Yeah. Okay, so anybody
they can raise their hand. You can see them.
So does anybody have a question on what the talk is about? Just raise your hand freely. Okay, let's go on to that. So let's try to define what is. So my focus is going to be on the first few words. So I have already explained what is motor drive for you, because this is what I think power electronic converter topologies. I think this is what is going to be more relevant for you than the motor drives. Okay, so I moved into that portion. Now I'm going to start with power electronic. Okay, I'm going to start with power electronic, and I'm going to show some example of power electronic converter, more examples of converter, and so that eventually what the topologies are, different ways of connecting the switches and so on and so forth. Okay, yeah. So let's get into that. First, let us start with what is power electronics. So you have power, you have electronics. Okay, in English, power has the meaning like authority, right? He's a powerful person. Okay, power of a bureaucrat, power of a minister, you have say all that. Okay, here what we mean by power is the physics power, the rate at which energy is converted from one form to the other, rate at which energy is consumed, rate at which work is done. That's all we call as power. And this power is in the electrical form. This power is in the electrical form. And what is electronics? The electronic stands or semiconductor devices. I think most of you are into this, and you certainly understand the semiconductor devices part very well. The only difference here is a typical semiconductor device for power electronics. Okay, the devices act in this as switches. The devices, I think I will probably make the pointer laser pointer option. That might be better. And typically the devices act as switches. Okay, in your case, there can be transistors which can act as amplifiers, and that can be in the linear mode when you are talking in analog electronics. In digital electronics, they kind of turn on and off and do a lot of things, right? In power electronics, they essentially act as switches. So when they act as switches, in the off state, they block a large voltage, and in the on state, they conduct a lot of current. Okay, so they are going to be working as switches, and they're going to be big, typically, not necessarily every switch. You have all sorts of ratings, and you do have devices which are rated up to 5 kilovolts. For example, Thyristors operating at 5,000 volt can block 5,000 volt. And we have IGBTs, which can block typically 1200 volts. And there are many devices that are coming up at 1700, 3300 volts, etc. And you have devices, which can conduct something like 1 ampere, few amperes, 10 ampere, 50 ampere, 300 ampere, 600 ampere. So there are devices of different current ratings also. So all that I'm trying to say is these devices are a little bigger. I mean, some of these can actually handle much bigger currents and can block much higher voltages than what you have, what you normally see. I'm just trying to take you from, give you this perspective of this, right? So whenever you have a question, please raise it, and you can shoot your question off. Yeah, you can even be free to just turn on the mic and speak. But yeah, that's also fine. So now what do we do with this? That's the question. We have electrical power and we have semiconductor devices. So what we do is we make the semiconductor device act as switches. Okay, and we kind of control or convert battery. Okay, battery, there may be battery bank of 48 volt, but it won't be perfectly 48 volt. It may be sometimes 49, 49.2, sometimes lower, etc. I may have in your room. You may have 400 volt, 3-phase, 50 hertz also, right? That may come to your building level, or that may be available. And in some places, they have 110 volt, 60 hertz, like in the US. And there are many other places where we have different kinds of voltages. But the utility will only supply some specific voltage to you. It's not going to supply one voltage for Rupam, another voltage for Rohtak, and Rohit, and so on and so forth. So you're going to get a common supply from that utility. So that's one part of the story. So it's going to be 400 volt 3-phase, or 230 volt single phase is what you get. Okay, or you will have power supply available exactly 12 volt, 48 volt, and there are also alternative sources. I'll speak a little more about it. So these are where power is available for you. But who needs the power? Okay, there are many loads. You can go on discussing this for a long time, what kind of loads, etc., etc. So I'm giving you some simple examples. Okay, you may have single phase AC load, or you may have 3-phase AC load. Okay, but they need to be well regulated. So what example, in the earlier, now the power supply situation is improved tremendously in the country. Earlier, there used to be a problem of low voltages. When we were kids, we used to have a problem of low voltages, and there's tube lamps won't work and many things like that. And we used to use what is called as voltage stabilizers very frequently. I think the faculty here might recall those very vividly. So we used to have what are called voltage stabilizers those days to do this now. So you need some kind of regulation always, and then it's going to work. It's basically AC load. And there are loads like DC motors, for example. Now the DC motor requires DC, and that is not directly available. So what you do? You rectify and produce DC. And how much value of DC? That again depends on that. So for example, if you are having a like say 200 volt DC motor, at 200 volt it will run near full speed. At 100 volt it will run at half the speed. So you will need some variable DC for its speed control. If you want it to operate at various speeds, you will have to control the voltage also. So it's not just a rectification. You need a kind of a controlled rectification where you can vary the DC output also. So this is a requirement of the load. Your DC motor is a load now. You have integrated circuits, and many of you are actually designers, and you are training to become designers of integrated circuits, microprocessors and all that. So these are very different loads. So some of them will have 15 volt IC. You have op amps which may be working at plus minus 15 volt, plus minus 12 volt, etc. You will have several ICs that work at 5 volt, and many other things now are working at 3.3 volts. And the processor voltage levels are increasingly coming down, as many of you would know, 1.5 volt, 1 volt, etc. And many of the very fast processors, okay, they consume very low voltage level, right? And they consume very high current. And some of you would be better aware of this than me. So where do you get your 1.5 volt from? Where do you get your 3.3 volt from? So your IC requires that, right? Your supply voltage is only a 230 volt 50 hertz. And sometimes you also have machines, for example, like X-ray and scanning machines, they draw huge amount of power in pulses. Okay, only when it is doing the scanning, or only when doing the X-ray, only when it's kind of producing a beam or some region, it's going to draw power, and that power is a huge pulse. Okay, so these are different kinds of supply, and there are different kinds of loads. So what you do is there is a mismatch between power supply availability and requirements. Okay, so sometimes the power supply may be AC and what you want is DC, so you go for rectification. And sometimes you may have a DC battery, but what you will have is an AC load. Okay, and so you go for what is called as inversion. Okay, you need to do this with many examples that you will see. And one thing that all of you would know is DC, there are no DC transformers. So if you need 100 volt and you have 48 volt available, you don't have a DC transformer. So you go for a DC-DC step-up converter. And there are no AC batteries. There are batteries are there, but a battery will give you only DC source. Okay, so this is my friend Professor Umanan puts this in a very interesting fashion. So, power electronics is there because there are no DC transformers and no AC batteries. And, not just that there are more things, but yes, these are very important aspects why we are trying to do that. Okay, then there's something more, which is more recent, and I would say that, I want to give you this now. So this is not, forget about the electric utility. You have many other sources of energy. Okay, now one of them is photovoltaic cells and array. Okay, I think since many of you are from the, devices domain, can I just ask this question if you don't mind? So I will just take a minute. Maybe I would just want to come out and check this out. Yeah, let me see if I can see your, have a small difficulty here. Okay. What kind of device is a photovoltaic cell? Can somebody tell me that? What kind of device is a photovoltaic cell? Anybody? Make a slide or anything for this, but I just wanted to, look at this, because, many of you are from a device background, so that's why I became curious about this. Okay, I'll put the question a little differently. Okay, kind of, how many of you are aware that photovoltaic cell is actually a kind of a diode?
Sir, solar cell?
Yes, sir. Sir, solar cell.
Solar cell, correct.
Solar cell.
Most of you will know that, right? Most of you will know that, right? Huh?
Yes, sir.
Very good. So what is essentially the difference between a diode and a solar cell? That's what I was just going to say. So, I'm going to use my hand now. Okay, since I cannot draw or something right now. So all that, many of you will know about this, but there are maybe some others who are not, very this thing. So it's just a general information because you're from the diode background. So you have a diode and you have the first quadrant current characteristic of the diode, which is an exponential characteristic, right? You have a diode voltage and you'll normalize the diode voltage with respect to some thermal voltage Vd by Vt, and it is an exponential function. So you will write it as some Is, an exponential function of Vd by Vt. So you have that going up now. So there is something called, you call that some voltage level you call, right? Cut-in voltage or something up to which the diode actually has very, very low current. The solar cell or a photovoltaic cell, what happens is, see, there will be very, very low current in a diode. Now, what they really do, I think some of you may know it even much better, and you can talk about that better. This is for those who might not know. So what you do is you push that to the negative second quadrant. You get my point? This is my horizontal line, and this is how the characteristic goes up. This is how my diode characteristic goes up. Now what I do is I intentionally push the characteristic down. Okay, the characteristic goes a little below the horizontal axis and goes up. I hope you can see me, right? So we do that. We do that by especially irradiating this, etc. with that. And it is this portion that is forced to go into the fourth quadrant actually becomes your solar cell. So solar cell is a diode. It's a very special kind of a diode, right? I think many of you might know about it, and probably you can look at it more on this now. So the characteristic is going to be something like that. So it's going to be a horizontal line and coming and hitting here. This is in the fourth quadrant. So we'll flip that up. We'll flip that up into the first quadrant, and that is your characteristic. So that is your characteristic of your photovoltaic cell, okay, a solar cell, right? So now that's not a constant voltage, that's not a constant current source. So you can get the IV characteristic like this. Okay, now I go back to what I've been doing. So you have a characteristic like that, and that cannot directly feed, okay, that cannot directly feed something. So what you normally do is there are other things. So you have photovoltaic power converters. So what you do with this photovoltaic power converters is typically you will use a DC-DC converter, and after that you will use a DC to AC converter and pump the power into the mains. I think I'll go into the full mode now. So you have that photovoltaic cell can convert photo thing and energy voltage level or at a frequency that you can use directly. So the power electronics once again comes in here. Then let's go into fuel cells. Okay, there are so many other things that are coming up here. Again, let me go into so you have fuel cells. These come from an electrochemistry side, and you have wind-driven generators. So wind drives blades and drives a turbine, and the turbine engine drives the generator. So the speed of the generator is going to be varying, and therefore its frequency is going to be changing. Okay, that's frequency is going to be changing. So what are we going to do about that? We cannot use unless it is 50 hertz. So we will have to do some power conversion in between that. So we may convert that into DC and maybe convert back into, so it will be a variable frequency AC. We will convert it into DC and we will convert that back into line frequency AC. Okay, and there will be waste heat-based turbine generator. So these are all, waste heat is there. So what you do is you try to recover that and use that heat to run a turbine, and the turbine is coupled to a generator. So since you are recovering something from that, the turbine may spin at some speed and it may be able to deliver some torque. So your generator may be running there. So you will need once again a power electronic converter. Its output may be some AC, but it may not be 50 hertz and it may not be 230 volt or 400 volt, and it may not be well regulated. So, but whatever output it gives you, you require power electronic converter, and you use power electronic converter to feed a load or to feed this power into the mains. Okay. And again, there is wave energy based turbine generator, not very popular in the country, but this is being tried out in a few places. So what you use is wave energy. You use very special turbines, which because of your waves, they spin. They have special kinds of blades, and the turbine spins, and from the turbine, there's a generator. So the generator is the reverse function of a motor. Motor converts electrical energy to mechanical energy. generator converts mechanical to electrical. So the mechanical power produced by the turbine is converted there, and that's what you do here. So all these generators will give you voltage, but that will not be at a proper frequency, not magnitude, and you use power electronic converters to use their energy meaningfully to supply a load or to pump into the mains. Similarly, you also have solar power concentrators. See, the photovoltaic cell is not the only way to use solar energy. Another way what you do is you concentrate solar power using some kind of focused cells and all that, and you store this in some kind of solution, and you store the heat energy, and you use this heat energy like waste energy, for example. You use this heat energy to drive a turbine and a generator. Okay, so all these give you electrical power at output. Photovoltaic cell, fuel cell, wind turbine generator. All these turbine generators give you electrical energy, but that energy is not in a useful form. And who comes and helps you there? It is the power electronic converters that come and help you there. So I was just talking about this in generic terms. So very simple one scheme that will work for you is convert this variable frequency AC. The output will be varying, magnitude, frequency will be varying, convert it into DC and invert it back to proper 50 Hertz AC, 400 volt or something at the mains voltage, and pump it into the mains. So that is why you will need power electronic converters. Okay, so I'm just coming out of this. Now at this point, I'm just curious if there are any questions at this point. We have just done an introduction. So, are there any questions at this point?
Sir, I have one question.
Go ahead, madam.
Sir, in solar cell, during the daytime, the solar cell power is it's getting converted from the solar energy, right? So during the night time, what happens to the converted part? Because that time the solar power is not active, means the sunlight is not there. So at that time, what happens to the converter? Like how the power is supplied to the mains?
No, the converter won't do anything. Okay.
So it is operational during the daytime only, or something like that?
Yes. So if you make a converter, a solar power converter, what is called as sometimes a PV, inverter or power electronic interface for a photovoltaic cell. It will typically contain a DC to DC converter, right? It will step up the DC voltage from some few volts to like a bigger volt, like about higher few hundred about volts kind of DC, and then it will invert and it will feed that power through a transformer into the mains. This will be operational during the day. If you have designed it only as this, it will not do anything other than that. So this is also people are trying to say that the power converter is staying idle. So what do you do? So there are some other solutions. So there are also some people who use the same converter, for example, to feed some things in UPS and something to charge and all that. That's a different kind of a design. So you try to have converters that do multiple roles. But in the simplest case, the simplest answer to your question is that converter actually does nothing. Once it goes below some threshold, typically they don't do anything. Does it answer your question?
Yeah, thank you, sir.
Yes. Any other question? How are solar power converters made? Priyam Pathak. Yes. So what you do is you actually have a DC to DC converter first. That's a boost converter. I'll just show that slide in a while. And then you will have an inverter. Right. So since you asked that, maybe I can just show you that straight away also. Wait a minute. So this is what you call as a boost converter. This is what you call as a boost converter. Now imagine this is your solar cell. And this side will be some other bigger capacitor or something. So this is a DC to DC converter. So the solar cell will be a kind of a variable voltage, etc. And this will be controlled in such a fashion that the effective resistance seen by this fellow will change. So what it does is it's a DC to DC converter, right? For example, an output like 10 volts or 20 volts, it can make it 40 volts or 50 volts or 48 volts or something like that, bigger than that. So it converts it into that now. And this DC voltage is converted into an AC, let us say, using such a circuit. I will show you this circuit. So this DC voltage is converted into a three-phase AC voltage, that RYB you see here, right? And now what you do is, after this you put a transformer typically. This is the most typical system. So there is RYB, there is a transformer, because you need some kind of an electrical galvanic isolation. So you put a transformer, and this will be connected to the primary of the transformer. The secondary of the transformer will be connected to the mains. Okay, the secondary of the transformer will be connected to the mains. Am I making sense, Priyam Patak?
Yes, sir.
Thank you.
Thank you, sir.
Thank you. Yeah, all right. So I'm not actually seeing that. By chance I saw that actually. Yeah, now I'm getting this tool better. Okay, fine. All right. So now what do I do here? I need to go back to yes. Why is it no, getting a small issue here? Just give me a minute. Okay. Now, no, not this. Okay, let me just reshare here. There's a small issue I ran into. Sorry about that. Okay. All right. Okay. Now we told why you need that. Okay, you have sources, right? These are sources of electric power, but they are only at certain frequency and certain voltage level. They are only at certain frequency and certain voltage level. And you have many loads, and their demands are different. And power electronic converter comes to bridge the gap between the two. Now, this is in the utilization of electrical power. Nowadays, power electronics is also used in generation of electrical power, particularly through alternative sources. And these are many examples that I have given you. So why power electronics is needed? So this is why power conversion. Now I'm going to say, like, what are the simple types of power conversion that you can look at? You may have a DC, and you might want to reduce the DC voltage from 100 volt to, let us say 10 volt or something like that, or 20 volt, 50 volt. So that is what is typically called buck or step down. And there is DC, and you might want to increase that, right? For example, you may have a 48 volt battery bank. You may want, to supply a 12 volt IC that requires power supply at 12 volt. So you need buck conversion. You have a 48 volt, but you might want to boost it to 120 volts to supply some load. Okay, so that you'll have a boost conversion. And you'll have DC, and you want AC to be generated out of that. So something like 600 volt DC will be there, and you will try to generate 400 volt or 415 volt three-phase AC out of that. Okay, so you have voltage source or current source inverters available for this now. Then there is AC to DC conversion. AC might be available for you, but like in your plug point, so in your room, your plug point has a 230 volt, 50 hertz single phase AC, and you might want a DC. Okay, you have your charger, right? So you have your laptop. Many of them do consume DC. So that's an example of your AC to DC conversion. Then there are many examples like uncontrolled rectifiers, phase controlled, Thyristor rectifiers, and there are active PWM rectifiers. Okay, these are all what you use using diodes, and these are some things using thyristors, and you can use them using active PWM rectifiers. So these are using MOSFETs and IGBTs and all the modern power semiconductor devices. You can build rectifiers, okay, which will draw very nice sinusoidal current. So the problem with these diode rectifiers is they will not draw sinusoidal current. They will draw very non-sinusoidal current from the mains and create what is called as harmonic pollution. Okay, so they will not be drawing sinusoidal currents, whereas you can actually make PWM rectifiers. That is, you can make rectifiers which can convert AC to DC, while the current drawn is perfectly sinusoidal and, also in phase with that. So this is all possible with power electronics. And in many of the power converters, the power flow can be unidirectional or they can be bidirectional. So these are some very typical examples of power converters that you will use now. So let me quickly give the very basic of what you're trying to do. Now I have a 10 volt supply. Okay, I want 5 volt. So how do I do that? One idea I have, I will apply 10 volt for 50% of the time, and again 0 volt for remaining time. 10 volt and 50 volt. So what I will get? I will, on an average basis, this is about 5 volt. If I do this very fast, okay, so fast that it doesn't matter to the load, okay, I'm fine with this. So this is what we do. So on an average basis, I can generate 5 volt. So if I want 6 volt, what do? I will apply this 10 volt for 60.6 millisecond and 0 for remaining 0.4 millisecond. So this is a basic idea. So I can use, for example, I have a coil that requires a 5 volt DC. So I will produce a pulsed waveform across this. So the average voltage is 5 volts. Okay. So what do I do with the ripple? The ripple will to some extent be eliminated, or I can always put some filters. I can put some filters to reduce this or something. So this is a very simple idea of how do you do a buck conversion. Okay. Then what do I do? If I have DC supply, I want to produce AC. Okay. Again, this is the simplest idea. So what I can do is DC supply is available, but I want 50 hertz AC. Okay. So what I can do, I will apply this for about 10 milliseconds. And I will apply minus V for 10 milliseconds. So what do I need? I actually need switches. I need a pair of switches to connect this directly across the load. I need to invert this using another pair of switches. So I can generate such a bipolar square wave. And this is not sinusoidal waveform, no doubt. But this is nevertheless alternating voltage. Okay, this is not sinusoidal voltage, but an alternating voltage. This certainly has a 50 hertz component. You can consider the Fourier series expansion for this. It certainly has a 50 hertz component. And there are some harmonics. You can ignore the harmonics, or you can try to filter the harmonics. Okay, so these are some simple ways by which you can do DC to DC conversion, DC to a lower value DC conversion, and DC to AC conversion. Okay, so some further refinement when I do this AC. If I'm AC, if I'm doing like this is a square wave, and if this is V, and if you recall from your Fourier series, the fundamental component of this, okay, here it is plus V and minus V. The fundamental component will be a sinusoidal wave like this, and the peak value of the sinusoidal wave will be 4 by pi times V. So 4 by pi is a little more than 1. It will be a peak like that. So I cannot control the peak value. So what I can do sometimes is I will apply pulses like this. Okay, I'll apply a set of positive pulses in the so-called positive half cycle and a set of negative pulses in the so-called negative half cycle. And this gives me another value of fundamental voltage, and I can control this fundamental voltage by controlling these pulse widths. So if the pulse widths become 0, I will get 0 voltage. If these pulse widths become full, that all the notches vanishes, right? It becomes entirely, it's about 5 pulses are shown. This is about 180 degrees. So if I take the pulse to 36 degree width, then this entire 5 pulses get merged into a square wave. So you can get a waveform as high as the fundamental as high as square wave voltage. So I can get all the way from 0 to 4 by pi V. That entire range is possible using this. Okay. The only trouble is now I can vary the voltage, but what happens? There are a lot of harmonics here. There are a lot of unwanted voltages which are still high here. So what I do is I go for some modulation like this. Okay. Width. I am modulating the widths of these pulses. Okay. I have a very broad pulse at the center and narrower pulses towards the side. So what happens? I still get a sinusoidal fundamental voltage at the output. I still get that, but now my harmonics are much lower. This fundamental and this fundamental can be comparable, or they can be made equal, provided I get the correct angles. The harmonics here will be much higher than the harmonics here. By doing this, I can reduce the harmonics very well. So that's all that I have to say. Are there any questions at this point of time? Are there any questions? I think if I move to that, I think I'm getting into some issues. So I'm not just moving there. Okay. So what is there in a power electronic circuit? So all of you would have studied, typically in a basic electrical engineering course. Okay. Even before you come to electronics, where you talk about diodes, transistors and all that, basic electrical engineering, there are only 3 elements: resistance, inductance, capacitance. Only 3 kinds of elements are there, right? Now, in power electronic circuits, what you have, other than resistance, inductance, and capacitance, you have something called a switch. You have something called a switch. Now, what does the resistance do? It dissipates power. Magnetic field. What does C do? Capacitance. It also stores energy as an electric field. Okay, as an electric field. What does a switch do? It controls the flow of energy. Okay, if the switch is on, it allows for energy to flow through. If switch is off, it will not. And the beauty of the switch is, ideally the loss is zero. Why ideally the loss is zero? A switch is a two-terminal device. It has some voltage across that and there's some current through that. When the switch is on, the voltage across the switch is very low, ideally zero. And therefore, the power dissipated is the product of voltage and current, and it is zero because voltage is zero. When the switch is off, there is no current. The current through the switch is zero. So if you ignore leakage, in many practical switches, you will have small leakages. If you ignore the leakage current, it is zero. So ideally, the current is zero, and therefore, the power loss in a switch is zero. So if you use switch, you will never lose power. You will lose very little power. Whether the switch is on or off, you will lose very, very little power. Okay, that's the idea why we use. So we need power conversion. And if we can use switches for power conversion, then there will be no losses in the switches. And therefore, you can achieve very high efficiency. So this is the reason for the twin questions that I asked some time back. So why do you need power conversion and why do you need switches? So this is the answer to that. If you switch, ideally the loss is zero, and any power conversion that is achieved through switches, it is going to have zero power loss. So the efficiency is going to be quite high. Okay, so I'm just going to now take you into this as to some of the switches. Are there any questions? Please raise your hand. Okay, now I'm going to give you a kind of a this a little slightly different model for switches, somewhat idealized model. So this is a diode, and the diode characteristic. The diode characteristic will be ideally, it will be in an exponential thing like this. But what we are doing is we are using the diode as a switch. Okay, so ideally the forward drop is neglected. So in an ideal diode, there is no forward drop. So what will be there? So V is equal to 0. So it will be on this line. So this is the on characteristic of an ideal diode. And what happens when the diode is off? You would have ideally seen there's a leakage current here. There's something in the third quadrant, which will go in the third quadrant. But for an ideal diode, leakage current is 0, and therefore you are on this axis. Okay, so this would be the ideal characteristic of a diode, or this will be the IV characteristic of an ideal diode, whichever way you can call it now. This is a switch. So when it is on, this fellow will be on one of these points here. That depends on the circuit. It may be here, it may be here. That depends on the circuit. And when it is off, it will be blocking some voltage. On how much voltage it blocks depends on the circuit. So it may be here or somewhere there. So this is a diode. And this would be the idealized characteristics of a diode. Okay. Now let me move into a power transistor. Again, I'm going to idealize the characteristic. If you look at the power transistor, the current, it's like a switch. It's a switch between C and E. Okay. So when I'm injecting base current, this switch is conducting. When I'm not injecting any base current, this switch is open. So when the switch is open, what happens? There is a potential. Okay. There is a potential, right? That C will be typically positive with respect to E, right? And that potential will be here, something like this. So there will be only a potential here. And if I don't ignore any leakage like this now, then what you would have seen as the on characteristics is, you would have seen in your electronics lessons and all that, this will be, if you call that as the collector current versus, VCE, right? IC versus VCE, you will see that it goes like this. Okay, it goes like this and it becomes flat like this. Okay, and if you change your IB value, it will be some other curve like this, and goes up like that. If you change your IB value to something higher, it may go like this, right? You will have this characteristic. Now, what I'm trying to say is, the flat portion of the characteristic will happen only when it is working as an amplifier. Okay, now this is only in the switching form. So it will be very close to this part of the characteristic, where you will have a VCE SAT coming here. What you will have is a VCE SAT coming here. Now, ideally, that VCE SAT is 0, and when VCE SAT is 0, the forward drop is 0, and this is going to be your ideal characteristics of a BJT. Okay, if there's a power BJT, and the ideal characteristics of the power BJT is this, right? Okay, now I'm going to look at, these are single quadrant switches. Why I call them single quadrant switch? This is a switch. Why this is a switch? It will conduct if IB is injected. It will not conduct if there is no IB injection. Okay, therefore it is on and off and it is a switch. But this switch only conducts, let us say, in one direction, and it is typically capable of blocking a voltage only when C is positive with respect to E. Okay, the reverse blocking capability, if any of the power transistor is very, very low. So it can block only this. And you can very clearly see here, this is a switch because it is on or it is off. But when it is on, it will conduct only from anode to cathode. And when it is off, it cannot conduct in the other direction. And when it is off, it will block only a reverse polarity, right? When K is positive with respect to A, only a negative voltage it can block. It cannot block a voltage in the other side. So when it is on, it will conduct only in one direction. And when it is off, it will block a voltage, but that will be only one polarity. K is positive with respect to A, right? And so we call these switches as single quadrant switches. We call these switches as single quadrant switches. Okay. Any questions at this point of time? Okay, I would move on. So how do I get two quadrant switches when I want them to conduct in both directions? If you take a power MOSFET, okay, it has an internal what is called as a body diode. So if I have to relate to you, what you normally have is a body terminal. So most of you are aware that a MOSFET is a 4-terminal device, because many of you from the devices background, there is also body. You have gate, you have drain, you have source, and you have body. And it is a very symmetric device, right? So drain or source can actually be interchanged in many of your transistors. Okay, but not so really in a power MOSFET. So in a power MOSFET, what they do certain shorting, body and source, something they get shorted then what happens is internally, you will start seeing a diode. There will be one back-to-back diode will be coming across drain and source, and one of them gets shorted. The other back-to-back, one of the diodes is visible here. And in power electronics terms, this is called a body diode. This is a body diode. And this allows for conduction in the opposite direction also. So this is a two-direct, it's actually inherently a two-quadrant switch, which can conduct in both directions. But this fellow can block only when your gate voltage is below the threshold, it is going to block. But the polarity of blocking was only when D is positive with respect to S. If S is positive with respect to D, it may start conducting in the other direction. So this switch is capable of conducting in two directions. So there is a bidirectional conduction, but it can still block voltage in only one direction. Okay, so this is your idealized characteristic of this. Now, typically, if you have a MOSFET, you call this ID and you have VDS. This characteristic will go up and will be like this. Now, what I'm trying to say is this portion you will never reach here because it's not an amplifier. It is only in the on state, so you will be only here. And if the RDS on of the MOSFET, the drain to source resistance in the on state is very low, it will be almost vertical line. So this is your idealized characteristic. And when it is off, it will be blocking like this. So it can conduct IGBT. This IGBT is a kind of a darlington of a MOSFET and a transistor. So, this IGBT can also conduct from collector to emitter typically. Here we intentionally put one diode called an anti-parallel diode. You put an anti-parallel diode and get this kind of two-quadrant switch characteristics. Okay. Yeah. So any questions at this point of time? Any questions? Okay. I'm handicapped because I'm not seeing all your faces. So, I don't know what's getting across. So somebody can ask, can I have a two-quadrant switch which can block voltage of both polarity, which may be conducting in only one direction? Yes. The answer is yes. You take a BJT or an IGBT, which typically conducts in this direction and blocks a polarity where the collector is positive with respect to emitter. Now, in series with that, you connect a diode. When you connect a series diode, it can still conduct from top to bottom in this polarity. But the voltage blocking, this fellow will be able to block a voltage where the C is positive with respect to emitter. This diode will be able to block, the cathode positive with respect to anode. So this can block voltage of one polarity. This can block voltage of another polarity. So together they can block voltage of either polarity, either positive polarity or negative polarity. So these are also two quadrant switches, and they are capable of bidirectional voltage blocking. So there is one naturally available switch that we call as, SCR or Thyristor, which used to be very popular in power electronics, and it's still popular when you go to very high power levels. So this, can do this for you. This is going to be a two-quadrant switch like this. Then I can go to four-quadrant switches. So what I can do, I can have a MOSFET, and the MOSFET has its own anti-parallel diode. I'm going to flip this around, and I'm going to conduct this. So here I can connect, this can conduct in all directions. For example, you can conduct from drain to source here, and then conduct through this diode. So there is a current from top to bottom. From bottom to top, it can conduct via, for example, this a transistor and this diode. So it can conduct in both directions. When it has to block voltage, okay, so when both these gates are turned off, they are below the threshold voltage, it can block voltage of either polarity. So this can block in one direction and this can block in the other direction. The same way with these two MOSFETs as well now. So again, I can use either BJT or IGBT and I can put one. So what I'm doing is I'm using the same thing. So this fellow can conduct in both directions and block only one. Now here I'm using the same fellow flipped around. Okay, this can also conduct in both the directions, but it can block in the opposite polarity. So by going for a series connection of these two, I'm going to realize a 4-quadrant switch. So this is a switch which can conduct in both directions when it is on, and when it is off, it will block either a positive voltage or a negative voltage. Okay, so similarly, you have some other example of how a 4-quadrant switch can be realized. So this is a an IGBT, or it can even be a BJT, and you have a diode, and this can conduct from top to bottom. This fellow can conduct from bottom to up, and these two are connected in parallel. So if current has to flow from top to bottom here, these are the two terminals of the switch. The current is flowing from top to bottom, it will flow like this. If the current is flowing from bottom to top, it will flow like this. Okay, and you can see that they can block either potential. So this is another example of a 4-quadrant switch, and this is yet another example of a 4-quadrant switch, which is entirely almost like a diode rectifier. And at the output of the diode rectifier, you have put some like a transistor or an IGBT. So here also you can see current can flow from left to right. This is one terminal of the switch, this is other terminal of switch. Current can flow from left to right through the diode, transistor and diode, and here. The current can flow from right to left through this diode, current, and back here. Okay, again it can block both the potentials when this transistor is turned off. When this transistor is turned off, okay, if this can be positive or this voltage can be negative, it can block. So this is another example of a 4-quadrant switch. So this is how we study switches, and then we come up with single quadrant, 2-quadrant, or 4-quadrant switches. And different applications, different kinds of converter circuits will require different kinds of switches. Okay, am I making sense? Are there any questions at this point of time? Yeah, because I'm not seeing you all. I think there is some comment there probably. Okay, fine. All right. So, are there any questions or comments at this point? Can we go on for another 10 minutes to take a quick look at what the buck converter looks like and what the inverter looks like?
Yeah, please go ahead.
Yeah, okay. Okay, fine. So I'm sharing this again. Yeah, somebody wanted to say anything? Okay, it says something. Oh, I'm sorry. All right. So let's look at first an example of DC-DC converter. So what I'm going to do as a DC-DC converter, so I have a voltage. This may be, let us say, 100 volts, and I want a load. Okay, I want this load to be 50 volts. The load requires at some particular point of time, the load requires only 50 volts. So what I have to do, I have to apply 100 volts directly to the load, and sometimes I have to short the load, so it is 0. So what do? I have a single pole double throw switch. I have a switch like this. This I call as pole. This is permanently connected, and throw. Sometimes it will connect it to this throw 1 or throw 2. Okay, this we call it as a single pole double throw switch in the electrical terminology. So there's one pole, there are 2 throws. When the switch gets connected to T1, the entire 100 volt will go across this. And when the switch is connected to T2, that will become 0. So you take the combination of the load and this inductor, take the combination of the load and this inductor. Okay, now you will get a square wave, and its average value is going to be lower than that. Now, you might ask why this inductor. Okay, many ways to explain that. For example, I want to apply a pulsed voltage. I cannot apply a pulsed voltage across a battery. I cannot apply a pulsed voltage across a capacitor, okay, which is sizable capacitor, not parasitic capacitances. It's a sizable capacitor. Anything that is voltage stiff, I cannot apply pulsed voltage. So we are going to do the buck conversion by applying pulsed voltages, and the pulsed voltage cannot be applied. The voltage across a capacitor, across a battery cannot change instantaneously. So what do? We put in an inductor. So the inductor takes the difference between the average voltage and the instantaneous voltage, and eventually that becomes a current ripple. So you put an inductor and you apply like this now, right? So then what you do? You need to realize this transistor. So how do you realize the transistor? If you start analyzing, you know when you have connected P to T1, what happens? When you have voltage applied like this, you will have current flowing towards the right. Okay, there's either plus VDC or 0. So you will have current only flowing to the right. Since the current flows to the right, through the switch also current flows to the right. Okay, that is why, through the current also. Now, this fellow is open. Pole to throw to, I'm talking of how do you electronically realize. So I will be putting another switch. Which is capable of blocking voltage with this polarity. Okay, now you take this transistor and diode. So you can see that when the transistor is on, it can conduct from its collector to emitter. Okay, like what I've shown here. And when the transistor is on, there is plus VDC coming across the diode, and the diode will be turned off because the diode is reverse biased. And the diode will be blocking voltage where the cathode is positive with respect to anode, like what you're seeing here. Okay, so I'm just trying to tell you how the transistor becomes a good choice and the diode becomes a good choice for this condition. Okay, we'll normally discuss this in great rigor, but here I'm trying to kind of keep that a little simple. And the same way, if the pole and the throw is connected here, okay, sometimes the pole will connect to throw 1, sometimes the pole will be connected to throw 2. So what happens? Now I am trying to see what switch will benefit me, will be useful for me. So when pole and throw 1 is open, it has to block, but it does not have to block with both the polarity, only one polarity. So if I put a transistor like this, and if the transistor's gate or base, whatever you call that, base injection or the gate source voltage is low, below the threshold, then the transistor is open. And the transistor is capable of blocking voltage where T1 is positive with respect to P. And the diode is capable of conducting. So when this is open, current will be flowing through this because of the stored energy here. It will continue to flow through this, and that is what happens and flows here now. Okay, so a way to realize this. So this is a generic way of showing that, and you have to realize. And how do you realize that? What you do is you look at the two states, P to T1 and P to T2, and you look at the conduction requirement and you look at the voltage blocking requirement. And based on both of this, you decide your switch, and this is how the switch comes. Okay, this is how switch comes, and this is your example of a buck converter. What you typically do is you will have some amount of ripple here, and when this is a load, when some kind of a passive load or so, what you do is you put an additional capacitor here so that the ripple in that is also bypassed through the capacitor. That's what you typically do. Right now, I want to do a boost converter. Okay, that's a little non-obvious. Buck converter I can do because I'm going to apply the voltage and I'm going to short. I can do this now. But boost converter is a little non-obvious. So one way to look at the boost converter is first look at the buck converter itself. So what happens in a buck converter? This may be 100 volt, this may be 50 volt. Okay, but if you look at I in and I out will be 2 times I in. I out will be 2 times I in. So how can you get that easily? So let us say you have these elements, okay, inductor. Let us say it is ideal. Let us say the transistor and diode are also ideal. There's going to be a small loss, doesn't matter. Okay, so your input power is equal to output power, or almost nearly equal to that. So what happens? V out by V in is I in by I out. So if V out is lower than V in, okay, V out is 50 volt and V in is 100 volt, what do you get? It is half. What is I in by I out? That is half. So our I out is twice I in. So when the output voltage is getting bucked, the output current is getting doubled. So voltage buck converter, when we say buck converter, that is actually a voltage buck converter. It is actually a current boost converter. Okay. So when I need voltage boost converter, what should I do? I should actually realize a current buck converter. So what is a current buck converter? And this is my current source, and I have a single pole double throw switch like this. So if I connect to throw 2, the current will flow like this. If I connect to throw 1, the current source will remain shorted. So I will have current pulses here. The current pulses has a DC component and it has a ripple component. Most of the ripple component will flow through this capacitance, and the DC component will largely flow through. The DC component cannot flow through the capacitor. It will entirely flow through this. DC component at a very small amount of ripple possibly will flow through this, and most of the ripple will flow through this now. So this will be a current buck converter, and this current buck converter, you can realize the current source can be realized by a series combination of a voltage source and an inductor. Okay, and this is actually a voltage boost converter. The only thing that you have to do now is the generic switch, single pole double throw, has to be put in terms of transistors and diodes. So this is actually a realization. If you go through a systematic procedure, so you will see that you will need a transistor between P and T1 like this, and you will need a diode between P and T2 like this. So you can see by considering the two cases and can come to this now. So this is what you look at as a buck converter and a boost converter. So this can reduce the voltage or it can increase the voltage. Okay, this does the role of, makes up for lack of transformer, if you will. So 100 volt can be made 50 volt, or 50 volt can be made 100 volt here. Okay, so that almost ends with our, buck converter. Are there questions at this point of time?
Sir, I have a small question.
Go ahead.
So when we talk about MOSFET, so BJT was replaced by MOSFET because it was not technology favorable, even though it has a better speed. So in terms of power devices, nowadays MOSFETs are being used as power devices. So is it more advantageous always in terms of that we talk about in nanoelectronics, MOSFET is better than BJT. So in power devices, how it is looked like?
Correct, sir. So what happens is, let us take, just where you are, right? Whatever I'm showing here, that itself. Okay. Now this can be a power BJT, or this can be a MOSFET, or this is what I've shown is actually an IGBT, an insulated gate bipolar transistor. Okay, yeah. So you are right. What is done is the MOSFETs are used. Okay, typically the MOSFETs are used. MOSFETs are the most common devices. If a power electronic engineer goes out of college, most commonly they will see MOSFET or they will see IGBT. So the MOSFET has, what you do is it works like compared to the older BJT, it is much faster and all that. And MOSFETs typically switch at several tens of kilohertz, the power MOSFETs I'm saying. And if you have proper, what you call a soft switching techniques, then you can use MOSFETs at about 100 kilohertz kind of things also, right? So you use a MOSFET. Okay, what happens with a MOSFET is the on-state loss of a MOSFET is, MOSFET behaves like a resistance in the on-state. You have the channel resistance, and you call this as RDS on in power electronics terminology. They call the on-state drain source resistance. So the loss is I square R. The conduction loss is I square R. Now I square R is a parabola. The parabola goes below a straight line, and then the parabola becomes very high, right? When the I square R, when I is very low, it is all right. But when I becomes high, what happens? I is high, and R, V into I, V is also high. So I square R is very, very high. So MOSFETs, to answer your question, MOSFETs are advantageous but at low currents. But when you go to higher currents, the I square R loss is very high because, it is I square into R, right? So that's the problem with MOSFET. So that is why the power electronics community came up with what is called as IGBT some 2-3 decades back. So this IGBT looks like a BJT at the output side. So the voltage drop does not change very significantly. The voltage drop does not change very significantly with respect to current. So this is more like a VCE SAT multiplied by I. So VCE SAT multiplied by I is a straight line, whereas I square R is a parabola. So at higher current, IGBT is advantageous. So what you use typically is you use MOSFETs at lower current values, and you cross some threshold, IGBTs become advantageous, insulated gate bipolar. Does it answer your question, sir?
Yeah. Thank you so much. You have explained so nicely. Yeah. Thank you.
So now the modern trend is you may be using a MOSFET. The MOSFET is getting replaced instead of silicon MOSFET. It is getting replaced by silicon carbide MOSFETs. Okay, or gallium nitride based FETs. That is a modern trend in very wide bandgap devices. So these are able to give you lower on-state and they can switch at very high frequencies. So from silicon, I think there has been a movement towards wide bandgap devices, particularly silicon carbide and gallium nitride in the power MOSFETs.
Okay, so another question is when we talk about silicon carbide for high temperature advantages, at device level, even though many people are talking about it, I also doing some work, but at fabrication level, it has many issues. Okay. So again, how it is looked in power electronics side for silicon carbide uses.
Yeah.
So is it really in application?
Yes.
Yeah.
Applications are started. Okay. So I would say that maybe about 10 years back, there were a lot of problems there, and there has been a lot of work to work towards the devices, university work, industry-based work, and university industry combined work, and many things like that. And now you have reasonably what you call reliable silicon carbide MOSFETs. See, what happens is you are coming from a microelectronic device background, so you are looking at the internals of a device. And I come from power electronic background where this is a bought out item for me, right?
Correct.
I buy this and I buy this with data sheets and all that. So what we do is we do some characterization, like, compared to other groups in our group, typically at IISc, that's also true about, our DESC. We try to understand the devices better. Okay, so we understand the terminal characteristics and work with that. So what we find is nowadays we are getting a lot of silicon carbide devices. Okay, they are not yet available at thousands of volts,
right,
and hundreds of amperes. Okay, but tens of amperes and a few hundred volts, you can certainly get a reliable silicon carbide MOSFET. Of course, the prices and other things may be there.
Yeah, maybe there. Yes.
Yeah. So that is available from the commercial ones.
Commercial point of view. Yeah. Okay. So, sir, will you take a break of 5 minutes, or would you like to continue?
I'm fine, but I don't know how, I don't know about the others. If you want, yes, we can just take a break for 5 minutes, and after that, probably in about 10-15 minutes, I can wrap up also. So, because I don't think I should push a little longer.
Okay.
Maybe it is 5:20, maybe 5:25, we can just reconvene, because many might want to just take a break.
Yeah,
and
sure.
5:40, we will kind of close. Yeah.
Okay. So, students will meet at 5 minutes. Okay. Thank you.
Thanks a lot. Yeah, we'll start in 5 minutes. think, can we quickly restart? I think maybe.
Yeah.
Yeah.
Yes, sir. Yeah, we can start.
Okay. So if anybody is tired, please raise your hands. Anyway, we can wrap up in 10-15 minutes. Is anybody tired?
No, nobody is tired. I believe it's so nice talk because I am also refreshing my knowledge on this.
Okay.
You have explained so nicely from the very beginning.
Okay, sir. Yeah, I think let me just go ahead and quickly talk about the inverter so that you can get a picture of what's happening there. So we looked at the DC to DC converter. So when we have some DC voltage and we want a lower voltage, we use a buck, and when we have DC and want a higher voltage, we use a boost converter. So let's look at, these are some things which you will see, how you connect the switches. These are some very essentials of power electronics. We have single pole, double throw switches. You see that the pole is always connected to an inductor or something which is current stiff. So here also there is a pole that is current to current stiff. So an inductor should never get opened out. So the pole will be connected either to throw 1 or throw 2. And if you see what is across throw 1 and throw 2, it is a voltage source which is voltage stiff and it should never be shorted. So here also what you find across the two throws is a capacitance which is voltage stiff and it should never get shorted. So this is something very fundamental to the power electronic converters and how the switches are connected. They are connected in such a way that the current stiff elements do not get opened out. So it has a path to flow either to T1 or T2, and the voltage stiff elements do not get shorted. So these are some basic rules in how switches are connected in power electronics converters. So that's what this says, and these all would be more relevant if you are actually closer into power electronics. So now I'm going to quickly take you through a single phase and a 3-phase voltage source inverter and possibly a current source inverter. So now I want an inversion. So what I'm trying to do here is, let me come back and see if I can put my pointer here. Yeah. So I have a load. Okay, the load wants AC. It may be a coil, it may be something, but the load wants AC. So what do? I use 2 single pole double throw switches as shown there. So one is connected here and the other pole is connected here. Now, when I connect this pole to the top throw and this pole to the bottom throw, the load gets a positive voltage applied across itself. Okay, the load gets a positive voltage applied across it. And instead, if the pole is connected to the bottom as shown by the dashed lines, here again the pole is get connected to the top as shown by the dashed lines. Now the voltage across the load is negative. It is no longer plus VDC, it will be minus VDC. Okay, so you can either apply plus VDC or minus VDC across the load. Not just that, if this is connected to the top and this is also connected to top, these two are independent switches. So this is top and this also to the if A is connected to minus and B is also connected to minus, load is once again shorted. Okay, the voltage is 0. So this inverter is a switching converter which can either apply the same DC voltage plus VDC across the load, or it can apply minus VDC across the load, or it can short the load. Okay, the load is presumed to be inductive and therefore it can be shorted. Okay, the load is not capacitive, the load is not voltage stiff. Okay, if the load is really this thing, then we put a series inductor also and make this like this now. So that's the presumption on the load, and we do this now. And this is an inverter, and this is a single phase inverter because you get only one AC. It's a single phase load, and that requires a single phase AC here. So how do I realize that? So if you can see that the current voltage across A and B is bidirectional, bipolar. Sometimes A is positive, sometimes B is positive. So the current can actually be flowing from A to B or B to A, right? And so this should be able to conduct in both the directions. Again, this fellow should also be able to conduct in both the directions. So all these 4 switches should be able to conduct in both the directions. On the other hand, when it is conducting, A is connected to positive, the potential here is plus, the potential here is minus. It is only plus VDC. This fellow never has to block voltages of both polarity. He has to block only voltage of one polarity. Therefore, what you do is you take switches like this. So this can conduct in both the directions, either through the transistor or through the diode. So it can conduct in both directions, but it will be blocking voltage of only one polarity. Let us say when this fellow is on and this fellow is on, current will be flowing like this. It can flow from A to B or B to A, but the voltage across the bottom transistor is always this A is positive with respect to negative terminal. Similarly, this fellow is off and the potential here is B is 0 and this is VDC. Okay, so you will not require only a unidirectional or unipolar voltage blocking, but bidirectional conduction. And this is a voltage source inverter. So when you make devices, you have to make these kind of devices. So these are all the challenges. So that's one reason I'm saying in power electronic, one of the critical requirements is the directions of conduction and then the directions of voltage blocking capability. All right. Now, what if my load is 3-phase? So instead of 2 single pole double throw switches, because my load is 2-terminal load, a 3-phase load is a 3-terminal load. So I put 3 legs like this, R, Y, B, and I connect my load across this. Again, these are going to be single pole double throw switches, and this is to be realized by a 2-quadrant switch which can conduct in both the direction and it can block voltage of only one polarity. So I'm going to do this. So the same kind of legs that I had in a single phase inverter, I just have to put one more leg. So this will give me AC. So because I can switch this, I can generate a variable frequency AC. If I want to generate 50 Hertz, I can generate. If I want to generate 100 Hertz, I can generate. If I want to generate 20 Hertz, I can generate. Okay, I can generate any sinusoidal frequency which is significantly lower by 10 times or 20 times the switching frequency. Say I'm having about 10 kilohertz, right? Something like up to 1 kilohertz sine wave, or a few hundreds of hertz at least, I can generate very nicely using this. So that's a 3-phase inverter. Okay, so you can just look at how a current source inverter is. So what happens here is you have the source and you have a load, and the load requires AC. This is a voltage source. Sometimes you will need a current source. I'm sorry, I have a small issue with my thing moving, or it's maybe a network problem. Something is not working here. Okay. So what happens here is, you can see, I have replaced the load by a current source. And this is my load. This is my load. So I have a current source inverter, and when here I can produce a output voltage which is actually bipolar. If the connection is like this, the current direction here will be positive. If it is the other way, if A is connected to T2 and B is connected to T1, the current direction will be negative. So the current that is injected here either can be plus I. If I call this current as I, it can be either plus I or minus I or 0. Okay, just as it could be plus V0 or minus V here, there it's going to be plus I, 0 or minus V. So this is what you call as a current source inverter. So some special conditions will use a current source inverter. So I'm not going into great details of this. So this is how you actually realize a current source inverter. You use an like an IGBT, and you use a series diode. So here you can see that you are using a unidirectional conduction but a bipolar voltage blocking capability. Okay, this has a bipolar voltage blocking capability. So this is another way of, I've just redrawn that inverter. If you want to make it a 3-phase inverter, you can put one more line and do so. But this is normally what you use as that. Now I'll just flash one slide and show you what is called as a multi-level inverter. So in these cases, what you use are only single pole double throw switches. The load can be connected either to the positive or negative. Sometimes we generate a 0 point. So what we do is we put 2 sets of capacitors and we have a midpoint, and we sometimes connect it to the midpoint also. So if you do this, then you can connect not only plus and minus here, you can connect plus, 0 and minus also. So you get additional voltage levels that are available at the output, and that is why it is called a 3-level, or then it's called multi-level inverter. The actual inverter will look like this. There is a lot of series of steps of deriving it. The actual inverter will finally look like this. Instead of you had 2 transistors, and with anti-parallel diodes, you will see that there are 4 of them, and these kind of 2 what are called as clamping diodes. So you use these as very high power levels and higher voltage levels. Okay, it's not a 600 volt DC bus, but something like you want to use a 3.3 kilovolt DC bus. Then it's difficult to get devices. So you go for such kind of things. So this is a multi-level converter. For example, this is a multi-level converter for 1 phase. You can do this now. So I'm not going to get into the details of this. Similarly, you can several levels, and here again, there is yet another configuration, what is called as a flying capacitor one. So here you use kind of charged capacitors, and using the charged capacitors, you generate various voltage levels. Okay, so that's something that, there are many other topologies. I think, that all that we may not actually require. So this is one leg of what we call as a flying capacitor topology. For example, here, like if both these transistors are on, I will get positive voltage, If both these are on, I will get this negative voltage. If this fellow is on and this fellow is on, so this voltage will get subtracted and it will come here. Similarly, if this fellow is on and this fellow is on, the voltage will get subtracted and will get 0 here. So you can get plus, minus and 0, just like your previous inverter, but here, using what is called as charged capacitor, which is not connected, and this has a funny name called flying capacitor, which basically means none of the terminals of the capacitor are really connected to a voltage stiff point. That's what it means. So all these are switching terminals. So that's what you really have now. So I think, I would just stop here. There are many topologies. So I think I've talked a little bit about that. I didn't understand the background quite well. Otherwise, I would have probably talked on a more device-focused talk. But only, I understood at the start of the lecture that more people are from that background. So I've talked about some things about the devices, how the power electronic engineers look at devices, and we looked at essentially DC-DC converters and looked at some part of the DC-AC converters. And many of these are probably, a little too high for this particular part. And I think I thank you for your patience, and any questions I can kind of answer now. Yeah, I'll try to come back.
Any questions from students?
Yeah, in which application current source inverter is used? Okay. Like one application I can readily think of is welding. Okay. So welding is one place where they use current source. What they try to do is they deal with very high currents. So the current source inverter has one advantage of shorting. It will not happen. So there is a current source, and it will not give you much higher current and things like that. So yeah, welding is one that I can kind of readily think of. So you would have seen those the welding sets that they use, and where there's an arc is produced, right? So any of those welding substances, they are current source inverters. And in the olden days, there were many current source inverters were used. Interestingly, okay. So since you asked this question, now like the question that they were asking, like now you use a MOSFET, and the MOSFET itself has an anti-parallel diode. So it is a bidirectional switch. So the olden days, Ananya Bhattacharya, they used thyristors. So thyristors were the power electronic devices available. A thyristor can conduct in only one direction, but can block voltage in both directions. Okay. Just like your MOSFET can conduct in both directions, but only block in one direction, thyristor is kind of its, it has its complementarity there. It is like dual. Thyristors can conduct in only one direction, but block voltage of both polarities. And such a switch is useful for current source inverters. So when thyristors were very popular, people were using current source inverters. Now with MOSFETs and IGBTs having become popular, voltage source inverters have become more popular. Okay, I think that's roughly how it divides. So you have very special applications where you need a current source inverter. So there is a very tight link between current source inverter and voltage source inverter and the nature of devices that are available. Whether you are having bidirectional conducting switches or you are having bipolar voltage blocking devices. Does it make it clear to you, Ananya?
Thank you, sir. Yeah.
All right. Yeah. Anything else?
Any questions from student side?
Excuse me, sir.
Yeah, go ahead, please.
Yes, Sam, go ahead.
Yes, I want to ask, what is the limitations of buck and boost converter in terms of power? Like, can we design even up to 10 kilowatt or something like high power like this?
Which converter you are talking of? Buck and boost. Which converter, Sam?
Boost converter, sir. Yes, sir.
See, power electronic converters are available up to megawatts and up to even 10 megawatt. Okay. The last converter that I showed you, like the multi-level converters are used at power levels of a few megawatts. Like about, I have seen converter up to about 10 megawatt, 20 megawatt. Okay. And multi-level converters are used in that power range of hundreds of kilowatts typically and a few megawatts. And lower power levels of inverters will be typically like hundreds of kilowatts and tens of kilowatts will be the usual single phase, 3-phase inverter that I showed you, 2-level inverter. Yeah. So power electronic converters can be there from very few power. That can be very small power supply. Like, it can be like point of load converter. Like, for example, you have an IC. So you can actually build a 3 watt or a 4 watt power converter. So power converters are there from that level, where it can be only a few watts and all the way to a few megawatts. That's the entire range of power converters you can have. Yeah. Does it answer your question, Sam?
Yes, sir. Yes, sir. Thank you, sir.
Okay. So Kabishri Hazarika has a question. Apart from silicon solar cells, which uses visible light as the source, are there developments of solar cells using shorter and longer wavelengths of sunlight like UV, IR? Can polymeric doping help? Actually, you have to speak to people who work more on the solar cells. I'm not very familiar with that. I'm familiar with solar cells, more from a power electronic point of view. So I only understand the terminal characteristics and things like that. In fact, I don't even work so much on the solar interface. My colleagues like Professor Vinod John, Professor Kaushik Basu, and others work more on the solar aspect of power electronics. I work more on motor control and machine side. So there are others who work entirely on photovoltaic cells. For example, we have a department called CENS, Center for Nanoscience and Engineering, and we have a department called Materials Engineering and interdisciplinary Center for Energy Research. There are many colleagues there. So they do different kinds of cells. I believe that all this will be possible. I mean, I cannot say much about that. Yeah. So many new kinds of things are certainly being investigated. I'm sure that UV is certainly being used at some level for many of those. That's what my understanding is. So I have seen UV, for example, in some applications like cleaning and something of that nature. There's one Professor Digvijay Nath who does this, and there are quite a few colleagues who are more from materials and devices background. Some of them devices background who do this. Yeah. Unfortunately, I cannot answer more of issues.
Okay, so there is another question in the chat box from Mr. Albert Demery.
Okay. With parallel MOSFETs, there are current imbalance between the MOSFETs. What is the best way to prevent that for high frequency application, active or passive? See, the best way is not to use anything other than that. If at all you have to use parallel MOSFETs, you're going to use only when you cannot get high enough current ratings. Okay, it is best to handle them through a layout. The circuit layout, the parasitics matter a lot in power electronic circuits. Okay, the circuit that is drawn on paper, okay, the same circuit can be realized in hundreds of ways in the actual circuit board. In power electronics, the layout matters. Power electronics is extremely layout sensitive. Okay, whenever you have parallel paths, you certainly have to ensure that the parasitics are not unduly different in the several parallel paths. So a lot of attention has to be paid to the layout. I think that is what we do. Otherwise, my students have been routinely at least having 2 devices in parallel, like silicon MOSFETs or SiC MOSFETs. Many of our power converters have 2 of them in parallel. We have not been seeing any issues. Mainly, the layout has to be as tight as possible with parasitics, etc. Today, I had never had a chance to do that. Maybe, as I said, I should have probably thought about a device-centric talk. I mean, I think I didn't understand all your background that clearly until I spoke to some of you. Yes, so I think that is what you actually have to do. Yeah. Very good. Ananya Bhattacharya has raised an hand. Okay, go ahead.
Yes. Sir, I have a very simple question actually. Sir, now like more electric vehicles are coming up this technology, and like with this new technology coming up, people are they are purchasing electric vehicles. So the charging station concept. So in a very generalized term, are they also a power converter like the charging station?
Yes.
How they are getting the power, like the charging station, how they are like from the mains or something, how they are getting the power?
They're getting the power usual from the 3-phase mains, and then they are actually the chargers may have a 3-phase or then single-phase input. And there may be, depending on the size of the charger, if the charger is only a 500 watt charger, 1 kilowatt charger, 500 charger will be only a single phase AC input. 1 kilowatt, 2 kilowatt will be sometimes single phase or sometimes 3-phase. Higher than a few kilowatts and higher, it will be typically a 3-phase. Okay, then there will be a power electronic circuit. Okay, the buck converter and the boost converter we saw and the inverter we saw are the very basic circuits. From this, you can build on many of them. And these are called non-isolated circuits, where the input side and output side, there is a common terminal. There is no isolation between them. And there is another class of power electronic converter called isolated power converters. So in between, you will have transformers coming there. So flyback converter, okay, and isolated forward converter. So these are all certain converters that you can use to go about doing it. Okay, so some of these are so they will use certain kinds of power converters. So what there will be there is, when AC is available, you will have an AC to DC conversion at some stage first. And many a times, what is called as with power factor correction or something like that, so that the input waveform is proper, etc. And then once you get the DC, then there is a kind of a DC-DC conversion, and that will charge. So that is how, typically charge. There are many configurations, many topologies are possible. Yeah, but the chargers are power electronics. In fact, I imagine that about 5-10 years later, in a basic power electronic curriculum, probably students will be learning mainly about chargers. That's my understanding. I mean, that's how it might code to. So you can have many things. Okay. So you will have, for example, an AC to DC conversion, and then there is a charging stage, something like that. So it's a power converter. Many possibilities are there. Yeah.
Okay, sir. Thank you, sir.
Yeah. Yeah. Somebody said something. I missed that. I think that was in the chat window. Some advantages of flying capacitor inverter. Okay. One of the advantages is that the layout is not that sensitive. For example, flying capacitor inverter is for a higher voltage level. It's a multi-level converter essentially. So if you look at the actual converter, maybe I should probably share that. Yeah. So if I make one leg like this, you can see there are many switches. And as I told you, power electronics is very layout sensitive. I'm showing this as like a short, but that's not a short. There are parasitic inductances, and these parasitic inductances are very important. They can, kill the devices also. So these are very, very important that we go about doing it now. So what we are trying to do here is basically how these devices are put together, etc. Okay. Now, relatively, if you say this converter, the layout is not that complicated. So these are two devices together. You can see these are two devices put together. You get such modules, and there are these two are simple. It's not that layout sensitive is one advantage probably I can say. But the flying capacitors are used much less. I think the correct man in the country to speak about is this one, Professor Anubrata De in IIT Roorkee. He worked with Professor Gopakumar there in IISc. He is actually a person who does his research on this flying capacitor, who used to do some part of work on this now. So one advantage I can think of is, that the layout could be much easier to build this leg compared to that. But maintaining this voltage at 0.5 VDC is the biggest challenge. Okay, in a flying capacitor topology. So you have to do your control appropriately, that this is connected to a DC supply, so nothing will happen to this. But maintaining this flying capacitor at 0.5 VDC or within at least 0.48 VDC to 0.52 VDC, something like that itself is a big challenge. Okay, I hope that kind of answers your question.
Yeah, thank you, sir.
Thank you. Yeah. Okay, all right.
Is there any questions from students? Yeah, one question from Brijesh.
Go ahead, Brijesh. What is the scenario of graphene batteries nowadays? Honestly, I'm not, very knowledgeable about that. The power electronic engineers have not still started seeing them. So lead acid has been there for a long time, and many people are talking of lithium ion, and lithium ion is kind of very standard now, and some variations are being proposed. So in most applications that I see, either in the industry or here, or we only have been seeing lithium ion or in lead acid. So whenever I step out on any site or something, these are the two I see. And the other thing that we are seeing a lot is ultra capacitors, are called super capacitors, which are somewhere between battery and capacitors. Okay, their capacities are so high. It's not in microfarads or thousands of microfarads. It's several farads, and they can store a lot of energy. And they come somewhere between batteries and capacitors. Okay, they can produce a lot of ultra capacitors and super capacitors. They are getting a lot of attention in power electronics. Yeah, I am not personally aware of graphene batteries much. Thank you.
Okay, sir.
Thank you, Brijesh.
Thank you, sir.
So if there are no other questions, so let us thank our speaker, Professor Narayanan. So you have speak so nicely, starting from the very basics. So it is really, really helpful and it is engaging. 2 hours, just through interview so nicely. Thank you so much for your nice talk. Thank you so much. And we hope to see you again next time, hopefully physically here in the campus. So thank you so much, sir. Thank you so much.
Thanks a lot, all of you. So
thank you. Thank you.
Best wishes to all of you. Thanks.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thanks a lot. Bye. Bye.
Bye, sir.
Bye.
Thank you, sir.
I'm signing off, Rupam. And,
okay. Thank you so much, sir. Again. Yeah.
Thank you.
So the students, so we have the last session tomorrow. See you at 4 p.m. tomorrow again. Okay. Thank you.